So let's find what we can. So we need to find state 2. We found state 1, we need to find state 2. So in terms of finding state 2, we know that P2 is equal to 500 kPa, and that V2 is equal to 2V1, so that's equal to 0.6752. So when we look up this value of the specific volume, so the value of the specific volume is over here somewhere, so you go in the 500 kPa superheat tables, you find out where this value is, and you're going to have to interpolate to find it. So we're going to need to interpolate and if we do that, we'll find that H2 is equal to 3402.3 kilojoules per kilogram. And now that we have the specific volume, we have the pressure, we have the enthalpies, we can find the heat, we can find the work, and we'll find the work against the surroundings. So the heat, so Q is equal to M times H2 minus H1 is equal to 0.5 times H2, 3402.3 minus H1, 2538. And we end up with that Q12 is equal to 432.1 kilojoules. Now let's find the work, and then we'll find the work against the surroundings. So the work is equal to the P times V2 minus V1, which is equal to P times the mass times specific volume 2 minus specific volume 1. So in this case, we're not using we're using the total volume, but we're recognizing that the properties we find in the tables are specific volume, and we're going to be using that. So let's substitute in, and we find that the work from 1 to 2 is equal to 500 kPa times 0.5 kilograms times V2 0.6752 minus V1 0.3376, and when we multiply this out, we get the work from 1 to 2 is equal to 84.4 kilojoules. So we have the work, and now we'll find the work of the surroundings using, now the pressure of the surroundings here is just P atmosphere. So the work against the surroundings is P atmosphere times M times V2 minus V1. So we have 100 times 0.5 times 0.6752 minus 0.3376. And when we do this, we have to work against the surroundings. So the work against the surroundings that we see is 16.88 kilojoules. And so now we have examples for a constant pressure process where we did it first for an ideal gas and now with the tables. And so this is an example of how to do it. And so we see how the substance can change, the process we go through, the methodology we use remains constant. Now we're going to continue with constant process closed systems. We're going to look at a constant temperature closed system. And let's consider a piston cylinder. And we'll have it expand, and we know that the temperature is going to remain constant. And what we're interested in is applying this to an ideal gas. If I look at an ideal gas, we know that PV equals MRT. And that's going to be equal to a constant because the temperature is constant. I could integrate and find the work of PdV and P is C over V dV. So we have that the work is equal to a constant times the log of V2 over V1. And C we see is MRT times the log of V2 over V1. If you notice that PV is a constant, then the pressure volumes are opposite each other. So I could have P1 V1 is equal to P2 V2, or I have that V2 over V1 is equal to P1 over P2. So I could take this, I could replace the pressure and put it in here. So we could do that. For an ideal gas, as we continue, we notice that delta U is equal to M C sub V, T2 minus T1, which for constant temperature is 0. So we end up with the first law of Q is equal to delta U plus W, or Q is equal to W for T equals C. So for T equals C, we have the situation where the heat is equal to the work. Let's do an example and put some numbers associated with this. So if I consider a piston cylinder as we did before, but this time we'll have it be air. We'll have it be 500 kPa initially, 0.5 kilograms. And we're going to let the temperature be 500 degrees K. And now we can apply, we want to find the work. So this is going to expand at T equals C until the final pressure is 200 kPa. So we're going to let it expand until the final pressure is 200 kPa. So when we do that, let's substitute in, and we see that the work is equal to MRT times the log of P1 over P2. And so we have 0.5 times 0.287 times 500 times the log of 500 over 200. So we've substituted in and we find that the work is equal to 65.74 kilojoules. And this is equal to the heat as well. So we have that the work and the heat are the same. Now let's just see why this does not work for a pure substance. We restricted ourselves to an ideal gas, and I'll show you very quickly why we had to do that. So if we look at the TV diagram for a pure substance, and our familiar line of constant pressure, and our line of constant temperature would go this way, but what if I were here at state 1 and then went out to state 2 there? So if I had it expand from there, in here there's equality, and you know from looking at the steam tables that there is a change of internal energy as the liquid evaporates. So we cannot say there is a delta U, hence W does not equal Q for a pure substance. Now let's consider a constant volume problem. So I look at a constant volume problem, which we've looked at previously. And we have a tank or something like that, so we have a tank. And we know for a constant volume problem that the PV diagram would be constant volume going basically from 1 to 2. Or on a TV diagram, if we had a pure substance, we'd be going from state 1 to state 2. So we know what the process looks like. And in this case, there are different ways that we have energy added to the system. So for instance, we could have panel work. So I could have a system where I have panel work, WP going in, and that would provide energy to the system, so we'd have a change of system state. So in this case, let's add a little bit more here. Let's pick 0.5 kilograms of air. We'll start off with 500 degrees K and 500 kPa, which I think will be my favorite properties for much of today's lecture. And so now let's look at the first law for a closed system, and we're going to have this be air. So again, we're looking at an ideal gas. So we have a closed system. The substance is an ideal gas. Q equals mRT. The process is V equals C. And so then we can write the first law. Q is equal to delta U plus W plus delta KE plus delta PE plus WP plus W electric. So in constant volume problems, there may be other work terms. So this is the PdV work. This would be panel work. This would be electrical work if I had a heater going in. So in our case, let this be, the tank is insulated. So Q is equal to 0. We're going to let WP equal 50 kilojoules. And so then we can simplify the first law equation, and we will eliminate the electric work, the change of potential energy, change of kinetic energy, nothing is being thrown. This is the PdV work, so that goes to 0. Q is 0. And basically, the first law comes down to that minus WP is equal to delta U, which is equal to MC sub B T2 minus T1. So in this case, I know this is a minus 50 kilojoules, and that's equal to 0.5 times 0.7176 C sub B times T2 minus T1. And we can solve for T2. And we end up with that T2 is equal to 639.4 degrees K. And then for a constant volume problem, so if I go back and look here, if I look at volume's constant, then T over P is constant. And I can solve for T2, I can solve for P2. So P2 is equal to P1 times T2 over T1. And if you substitute in, you get that P2 is 639.4 kPa. And the reason the numbers are the same is that I picked 500 for both of them in their proportion. If I were to look at this for a pure substance, and I were starting out here at state 1, so if I were starting at state 1, I need information about state 2. In this case that we had, I didn't need to worry about it, but in the case of a pure substance using the tables, I need additional information. So I need additional info besides V2 is equal to V1, such as I would need to know P2 or something like that.